Okay, so I'm making this hopefully short little video here to talk about an alternate graphical way of doing geometric constraints, or at least solving for degrees of freedom for any specific scalar or whole sketch using a graphical method. This will be very similar to the graph-based ways of solving sketch the constraints altogether. But anyhow, this is fairly simple, very similar to the graph-based solutions. But anyhow, instead of using a point by itself, including two scalars that just get lost in the mix, we're going to use for every entity all of its scalars and have the constraints going specifically towards them. So the rules here for these graphs are that the nodes, or in this case the circles, are individual scalars. The edges, or directed arcs, are the constraints. You'll notice that the constraints do have a direction that they point. The direction that they points from the parent or the object that is dependent on to the thing that depends on it. So the way that this reads is P1y depends on P2y. So we don't really need the equation for it here. We're just going to solve for now for degrees of freedom. So another set rule is that a single scalar can have no more than a single directed arc pointing at it. It doesn't matter how many are pointing away from anything, but only a single arc can be directed to a scalar. And we can reorder or change the direction of the directed arcs to any of these that are compatible to meet the previous requirements. So here we have this figure, which is a rectangle, horizontal, top and bottom, vertical, left and right, and a length constraint on the top and on the right. So here we can see these constraints here are applied in a way that is valid to this system. So here, for example, we can see the horizontal constraint on the top says that P1y depends on P2y. So that's the only valid combination for that particular constraint, is from y to y on those 2 points. But the direction can be changed to solve other problems, as I'll show later. Okay, but this length constraint, it could go either from P1x to P2x, or P1x to P2y, or P1y to either of these other two. So any of those 4 combinations are valid for it, just as long as we meet the requirements of only a single directed arc towards an entity. Okay, so here we can see that the graph is set up in a way so that we see that P3 is fully under constrained. And we'll notice that this is going to be considered a rigid body here, because only 2 degrees of freedom remain, and specifically we can fix them to a single point. So if we were to grab P3 and move it, if we were to send everything to the solver, it would act like a rigid body. But taking advantage of that, we could just sidestep the solver. We know that we have degrees of freedom here, and we can move them around. There may need to be some double checking later if a point's not reachable, but we'll see about that later. Anyhow, we could move this around as a rigid body, and we wouldn't really need to solve for the rest of these points. We would just translate them the equal amount of the change in the x and the y of this one. Okay, so that's fairly simple. Now, if we wanted to move, say, P2 instead of P3, we'd grab P2. We'd want to change these so that P2 doesn't depend on anything else. So, for example, this one we'd want to switch the direction of it, the direction of the dependency, as well as this one. And in this particular case, we can actually move the dependency for x to any one of these, and the same thing for y for any one of the y's. So now we could move this one around, and it would still act like a rigid body. Now, the parameters are yellow because there is no fully constrained point yet. Even though these scalars are constrained, nothing is pointed to by a properly constrained point, or a point that is connected to something grounded. So down here in this next one, we have here The ground is represented as a mechanical ground. We're going to fix P2, both the x and y component. So we draw an arc from ground to the point. Anything from ground has to go from ground to whatever it's constraining. The direction cannot go the other way. That doesn't make sense. Anyhow, we'd have to reorder any constraints to point away from it, so there's only a single line pointing to each scalar. But here we can see now it's properly constrained. This cannot move no matter what. It's grounded. It's grounded. And because it's properly constrained, any scalar that these properly constrained scalars point at becomes properly constrained, and that dependency follows through the rest of the entire thing. So if we were trying to move a point here, we wouldn't even call the solver. We would just, perhaps the cursor would show something showing that there are no degrees of freedom remaining to move that point or entity or whatever. Okay, so that's that idea. Originally, up here with our rectangle, we had the length of the top on the right-hand side constrained. Let's look at the possibility of changing, instead of this length constraint on the right-hand side, let's have a length constraint from P2 to P4. Let's go down and look at that. Now we could have drawn this without knowing anything about this system. Go from P2x to P4x. And if we sat down and thought about this, it wouldn't work because of the way that it's configured, that this is horizontal and this is vertical. But we can see that we can show that that's not going to work, because we have 2 points, there are 2 lines directed here at P4x. We're going to try to reorder dependencies to make this work. Well, we'll notice here that this directed arc, if we switch its direction, we'd have to switch this one's direction, and then we'd try to switch the direction here, but this one cannot change because it's coming from the ground. So we'll notice that this is not redirectable. The horizontal constraint, because this one is already taken up, is going to make it so we cannot have this length constraint go to this parameter. So instead, we'll have to have it go to y. So now it's properly constrained. Every scalar has a directed arc pointing to it, and nothing has more than one directed arc pointing to it. The last thing I want to show is, well, what happens if we get rid of L2? Well, we know from previous experience and just thinking about it that if we get rid of L2, well, I changed this just a minute ago. It used to be L2 was pointing here at y, and this was pointing the other direction. If that were the case, then the P4y would be under constraint. And we'll notice here that if we think about this, if you've got a vertical, horizontal length, and fixed point constraints, the only thing that we could move is either P4 or P3 up and down in the y direction. The x's are fixed because of the constraints that are applied, but either P4 or P3 would move up and down. And they'd move up and down the same amount because of this horizontal constraint. But we'll notice that we can change the dependency here so that we can move it. So if we wanted to move P3, we'd click on it and we'd reorder the dependencies real fast. And we'd recognize that we'd be able to move it up and down. Now the way that we'd solve this, the only things that we'd send to the solver in this case are P3 y and P4y as the parameters, and the only constraint that we send it is this horizontal constraint. So it simplifies the problem. All the rest of these points are going to be static because they're not involved. And we notice here that we cannot reorder this dependency here either. So the x is constrained. But if we wanted to move P4 instead, we could change the direction of the arc. Oops. I'm not going to change the colors, but the colors here would change, and this one would become under constraint. And in this case, we'd move it, and again, only send P4y and P3y in this constraint. So that's it. It's really basic. I do have, I've been thinking a little bit more about arcs and circles and things, but not quite ready to share those yet. So hopefully this video worked out and